Ever wondered how robots make these fast, smooth and powerful movements? And can you use that same tech in your own DIY projects? Well, some creators already are. And it's not a secret. It's called FOC and you can buy it off the shelf. But the problem is price. So if you want to build a regular quadruped robot, you will need 12 drivers, one for each motor, which is pricey. But what if I told you can get almost the same power as a top ODrive model for just 1/7 of the price? And for this, we will turn to every engineer's favorite tool. AliExpress. Let's type MKS XDRIVE Mini, it's Chinese ODrive 3.6 replica and it looks really good on paper. 3 kW of continuous power, wow! So I ordered 3 of them to test. Alright, let's see what we got here. Okay, let's have a closer look. This is DC connector, motor connector, break-in resistor, some capacitors, termination jumper, boot, reset, CAN, Hall, SWD, GPIO, SPI, and USB. USB feels pretty solid here, but I think you need to 3D print something to hold it because eventually it will break. On the other side, we see encoder, and let's take off this plate. So we can see a thermopod. And this plate is working like heatsink. Okay, let's zoom in. And here we have STM32F405, DRV8301, AS5047, 5C612L MOSFETs, and 0.5 milliohm shunt resistors. And now I want to get rid of this connector, because it's really bulky and we really want it to be slim. So by doing this, we just easily cut the thickness in half. Ta-da! Okay, now let's switch to CAD. Now I will just briefly design the thing itself, some case for it, and a motor mount. Some might say this is too much detail, but I found it's actually faster in the end for keeping the design tight and slim. I'm using a canvas technique here, which allows me to transfer all details without a caliper. Usually I just put PCB on the floor, hold my phone high and use the optical zoom. By centering the object in a frame, you basically eliminate all lens distortions. This keeps error under 0.5 mm, which is plenty of precision for case. Here I've created 2 versions, both with the original connectors and with XT60. After modeling a backplate, I've also added a motor, nice arrow for showing position, motor mount and case for holding that USB connector. And now, let's assemble this thing. Alright, it's starting to look pretty nice. I also added a break-in resistor, just double tape it on the side, cause in final version we won't need it, we will use regenerative braking, so it's temporary. Now let's power this thing on. Ideally, we'll see the motor start moving, and then it probably stop and throw an error, since we haven't actually set any settings yet. Next step, software. Let's install what we need and set this thing up. You'll find all the links, settings, 3D models, basically everything you've seen in this video on my GitHub page. I've put that link in the description. And just a quick note, this video isn't sponsored, I bought everything with my own money, I'm trying to make it as helpful as possible, so hit like and subscribe, it will really help. If you want, you can slow down this part to see like all installation process, but it's really simple. And also there is a text instruction on my GitHub. Now ODrive tool is loaded, we connected a USB cable and we can power it up to see it's connected. Then we will need to open myconfig.json file, it's on my GitHub, same link. And we will need to copy-paste every line from it, line by line. We start with erase configuration line, and config is pretty universal. So, if you use a different motor, you only need to change pole pairs count. Now it's set to 20 and you just need to calculate how many magnets on your motor you have and divide it by 2. Then copy, paste, enter line by line, as you can see right now, just to the moment when you will need to calibrate it. Starting from this command, you will need to wait until motor make a beep sound. Let's have a look. That was a terrible sound. Now just quickly confirm motor calibration is true. And the next command will be encoder calibration, and we also need to wait after it. It will not make any sound this time. So just when it stops, wait a couple seconds and continue. So encoder is calibrated and we continue line by line until reboot command. And after reboot command, it will do encoder sequence again. And now it hold position. Well, it weakly hold position, but we will turn it, no problem. Now let's try to spin it. I'm copying input position command and it will make 50 turns clockwise. And get back to zero position. 50 turns counterclockwise. And stop in the same position. That last command, axis state idle, just disables the driver output and motor stop holding position and doing anything. For tuning, I will show you another tool that we can also use instead of console. As usual, link will be on my GitHub in the description. This is a project by Moonlighting Pi, and he basically created a modern, web-based graphical interface for legacy ODrive firmwares. Installation is simple, just go to Releases and find .exe file. Then just launch it and it will open graphical interface in your web browser. I've connected the driver and now we can see the dashboard with some parameters like current and temperature. Not everything is working, since the driver uses slightly different firmware and doesn't have temperature sensors. Now let's switch to Inspector tab and I will show you what we need to tune and how to do it. Basically, from default settings we have significant overshoot and a pretty weak position holding, like it jiggles around the set position. And you can see how far it overshoots. Great news is that adjusting the driver is easy, you can just tweak it by feel without diving deep into control theory. I quickly pin it to favor its parameters that we will need, and the first one is position input. It allows you to move the motor. Number represents how many clockwise turns it will make. So for 6.5 number, it will make 6.5 clockwise turns. And if I hit 0, it will go back to 0 position, in this case making 6.5 counterclockwise turns. You can click the checkbox to the left of a variable name to plot it. Let's select position estimate. Now let's increase position gain. You can do it by dragging the slider or by clicking this edit button to put a number directly. Let's see how this works. Position gains control how aggressively the motor reacts when it's off target. Higher gains mean faster correction. Now let's try to remove this overshoot. For this we need velocity gain. It applies damping proportional to speed. But be careful with this one, only change this value in small amounts and don't hold the motor in your hands like me. Let's see what happens with overshoot. You see? It's that easy. Of course it's not a perfect tuning, but there is no such thing as perfect tuning. It's more like, does it fit your task or not? Now we just need to hit save or it will go back to the old settings after reboot. And here we have some bug. I forgot to press disable motor button before hitting save. But I just clicked multiple times and eventually it allowed me to save the settings. So the tuning is ready, and now let's try to connect it with some Arduino board. I made this simple schematic for you. One problem I faced was that the CAN model didn't work. Eventually, I found a mistake in its design. The resistor value was chosen too high, which causes the driver to stay in standby mode all the time. The fix is pretty simple, just desolder the resistor and short the pads together, essentially making it 0 ohms. And now I will quickly show you how to set up everything for Arduino-based boards. Okay, first I need to go to Arduino IDE. If you use ESP32, install this by Espressif Systems. After that we need ESP32 CAN implementation by SoriQK and ODrive library by ODrive Robotics. When all this installed, we go to Folders, Documents, Arduino, Libraries, ODrive Arduino, Source, and in this folder we need to download that adapter. Yeah, and put it in this folder. Yeah. So after that, our setup is complete, and we can navigate to examples and try some simple CAN test. Okay, let's actually copy this code, paste it in Arduino IDE, and hit upload. It's official, and by the way, the only one code example for Arduino. We just make an adapter for our hardware. And as you can see, it's working, but it's pretty boring, so let's go straight to adding a second driver. Connection is pretty simple, just don't forget to remove one of the jumpers. Next we go back to the GitHub, open examples, and find CAN ID Finder, copy-paste it to Arduino IDE, and upload it. This script doesn't control the motors, it simply reads and shows the CAN IDs. Surprisingly, we see in 4 CAN IDs, even though there are only 2 motors in the system. This comes from legacy code that was never fully removed. Historically, an ODrive setup exposed 2 motor interfaces per driver, and that behavior still shows up here. Fortunately, this is an easy fix. We connect the driver to the web interface and set axis 1 node ID to 63, which puts it into listen-only mode. So, we connect to the driver, open the command console, and then copy-paste this command from my config.json file on GitHub. In this case, I'm using 60 just as an example. It's active, but it sits at the very end of the node ID range. You can't use the same active ID more than once, but you can have multiple nodes set to 63, since those are listen only. Notice that I'm using a non-default CAN baud rate set to 500 thousandths, so you'll need to apply the same settings if you want this code to work. Don't forget to apply save configuration command. And by the way, the reason we're doing this is that CAN node ID 1 is already occupied by a ghost driver on every unit. If we don't change it, we'll get CAN conflicts due to duplicate IDs. It took me quite a while to figure out why one driver worked, but adding a second one didn't. Now let's do a real test with 2 drivers. Head over to the GitHub page and copy the next example called motion link. This is a one-way link where one motor acts as a position source and the other motor follows its motion. So let's try it. Oh, this is so satisfying. Yeah, it feels like super high resolution scrolling wheel or like a joke wheel on a video editing controller. And you can see a motion delay, and it can be more responsive or more smooth, depends on your tuning. This is so nice. Nice. I also decided to add a heatsinks. I bought some standard sizes from Amazon and cut them with Dremel like this. Then I placed a thermal pad on a MOSFET's heat dissipation pads, added a bracket and installed the heatsink. Now let's add some mounting point. I add 0.01mm splits between the mounting holes so the slicer generates extra walls around them. They fuse during printing, adding strength without increasing infill. I've also added a chocolate bar pattern on the bottom to relieve some stress during printing. Here you can see how it looks in the slicer. Next, I've added the T-slot aluminum profile and the mounting bolts, and we're ready to assemble. And we're ready for testing. For this test, I'm using the same motion link setup again. It's incredibly convenient and honestly way too satisfying to play with. I literally can't stop. I'm also using a kitchen scale to measure the torque. I've set the current limit to 50 amps, which might be a bit high for this motor, so I'm using a thermal camera to watch the temperature. $100°C in 10 seconds, that's too hot. But let's check the torque. With a 30cm level arm and a 675g load, the torque comes out to roughly 2 Nm. After reducing the current limit to 25 amps, it now produces about 1.2 Nm of torque, which isn't great, but this is a 160 kV motor and it should be much better with a 90 kV motor, but I don't have one right now. But this video is not about motors, so let's check how driver handles this load. As you can see, the motor overheats much faster than the driver. I've also checked the MOSFET temperature directly with a wired sensor and they remain cool, which means this driver can handle a much bigger motor. I recently got some bigger motors, but I can't fit them into this video or I'll never finish it. If you want to see me test them, like and subscribe and comment below if there is something specific you want me to try. Like this $250 90 kV motor from T-Motor. I want to keep this channel focused on cheap robotics, but I'm really interested to explore the gap between the cheapest motors and one of top-tier ultra-efficient options money can buy. I've also got this bigger no-name motor. I only know it's 100 kV and it's more than twice as thick as my Lay A308, so maybe this one will be enough to blow at least one driver and really test the limits. I'm still waiting for the 90 kV version of this Eagle Powers motors to arrive, and I'm thinking about making things more interesting, maybe a test where the motor launches gym barbell plates and I measure how far they fly, just to make it more exciting. So, after a couple weeks of testing this driver, here's what I learned. Does it work? Yes. Is it a pain to set up and tune? Also yes, but with the guide I've shown you, that hurdle is mostly gone. And if you're building something like a robot dog, there is a huge benefit here. You can transfer your tune settings to multiple drivers with just a couple of clicks. You don't have to suffer through the process 12 times. The power headroom is actually impressive. It's more than enough for what I'm doing. And honestly, I can push more current than most of my motors can handle. This gives me an interesting idea. I might implement a boost mode for the robot dog, where we crank the current limit to the absolute max for 5 seconds to allow a massive jump or a backflip. Multi-node CAN setup was working fine, as long as you disable that ghost node I mentioned earlier. The only real trade-off is lack of CAN FD, essentially just a faster CAN protocol. So, is there even a reason to buy the $90 ODrive micro if it's also like CAN FD? Well, only if you need a tiny footprint. In any other case, if you have the extra budget, just go for MJBot's Motos. If not, stick with me and these cheap wonders of AliExpress. And speaking about wonders, I can mention this one. This is STM32 Dev Kit, and it's only 20 bucks. Even after adding $5 for an external encoder, you're still looking at a dirt cheap Fox setup. But it doesn't work out of the box. Even with all the examples from open source libraries like SimpleFog, it's a massive struggle. I spent hours trying to get this to work with SPI encoder and had zero luck. It's a classic case of a great hardware without a software. But maybe I'm missing something. I just heard there is a mini Cheetah firmware port for this board. If you want me to try it, just write Cheetah in the comments. In the next videos, I'm going to test some 3D printed gearboxes with this motor and driver combo. The goal is to create the ultimate budget robotic actuator, or to see how 3D printed gears fall apart miserably. Honestly, both results are pretty exciting for me. Thank you for watching, and I'll see you in the next one.